Hello everyone, today we'll be doing problem number 14. It reads, two hollow concentric conducting spherical shells have radii A and B respectively. The outer shell is grounded and the inner shell has a charge plus Q spread uniformly over its surface. A. Sketch a graph of the E field of the shells from R equals 0 to R is greater than B, where R is measured from the center of the shells. And B. Recalling that grounding means zero potential for the object grounded, begin with delta V equals negative integral of E dot ds, and show that the potential of the inner shell is that. And C. What is the potential inside the smaller shell? All right, let's start this problem by drawing a diagram of the one that was given in the book. So here's your outer shell, and here's the inner shell. And here's A, and here is radius B. And charge plus Q is distributed along this surface. And so part A wants to know what is the E field from they want you to sketch the E field from here, all the way to infinity. So let's just do a quick sketch. So on my x-axis, I will have the distance or radii r. I'm going to say this is A, and that's B, and this will be the E field. So one very important thing to note is that these things are shells. They're shells and they're not spheres, so there's nothing really inside those shells. That means this plus Q charge is distributed on only the surface. And even if it were a sphere, they told you that it was conducting, so the charges would be on just the surface itself and nothing would be in the inside. So what does that really mean? It means that if you set up your Gaussian surfaces here, your E field will be 0 since the charge enclosed inside is 0 because there's nothing in there. And since this is a shell, there is nothing from this point here to here. So from 0 to A, you just have nothing. But then from A to B, first of all, since the very second you touch that surface of the shell, that's when you're going to start encountering your charge. And since it's really thin, it's not distributed like along a thickness, or it's not specified like that or something like that. It's just, you just shoot it right up, because instantly when you touch that, you're going to encounter your charge and you're going to get your E field. And then from A to B, we want to know what this relationship is. So let's try and figure that out. Let's start with Gauss's law. Surface integral E dot dA equals charge enclosed over epsilon. So if we're talking about between A and B, we're talking about where this dotted line is. This is the area that we're concerned with. That means I want to set up my Gaussian sphere right here, my Gaussian surface, and I'm going to use a sphere. And the surface area of a sphere is 4 pi r squared. And this will work. It doesn't matter if the sphere is this big or this big. It doesn't matter, because it's all the same between A and B. There's no space here, so it wouldn't matter where I set up this Gaussian sphere. All I want to know is right there. So E 4 pi r squared equals, and the charge enclosed this Gaussian sphere is just plus Q. So I'll write plus Q over epsilon. I'm going to solve for E, and I'll get Q over 4 pi epsilon r squared. And what is going to help us distinguish this relationship right here is going to be the r squared, because we're concerned with the radius. So I'm going to pull out 1 over r squared and leave all the other constants out there. There's a variable, and this will tell us, oh, well, what's that line going to look like? You just stick it in your calculator, and oh, it looks just like that. And that's part A. This is your graph. Okay, let's do part B. Recalling that grounding means zero potential for the object grounded, begin with this and try to get that. So let's begin with this. Delta V equals negative integral E dot ds. So let's begin with what we know, and that is the electric field, which we found in part A. So negative integral 1 over r squared multiplied by Q over 4 pi epsilon. So let's move all the constants outside because we can. Negative q divided by 4 pi epsilon integral 1 over r squared. And what are our limits of integration? Well, if we are trying to find the potential of the inner shell, then we are mostly concerned with just like from here to here. Going from here all the way to infinity is not going to be very helpful. And also what another big hint is that right here, there's a bunch of a's and b's. Well, the limits of integration ought to be a to b then. And so now you got to take the antiderivative of this guy. So to do that, you can, give me a moment. To do that, you can rewrite r 1 over r squared to r to the power of negative 2. And the antiderivative of that would be plus 1 to the exponent. And you add a negative here. If you take the derivatives and matches out just right. And then you write your limits of integration. That works out fine. And now all you got to do is plug in b and a and start solving this. Negative q over 4 pi epsilon multiplied by 1 over b minus 1 over a. Do a little fraction addition, subtraction. Basically multiply both top and bottom by a, and over here top and bottom by b. You can add them up. You end up getting a minus b over ab. And also, I should have mentioned, but the negatives here and here will cancel out. And finally, your answer here, they want in kq. Well, k equals 1 over 4 pi epsilon. So you got that, and then you got q. So you got k, q, b minus a over a, b. And this matches exactly what we got in the book. And this is how you do part B. Let's see, yep, we got it. Let's do part C. What is the potential inside the smaller shell? So what's the potential right here? Well, let's see what we got. We're gonna start with delta V equals negative integral E dot ds. Well, let's look back right here. We know that since this is a shell and not a sphere, the E field inside the inner shell will be 0. So we know that is 0. So we'll do negative, and the limits of integration, since they want just what's inside the smaller shell, it's going to be from 0 to a. 0 to a multiplied by 0 dr. Well, that doesn't give you much anything at all, right? It's just delta V equals 0. But delta V itself is actually the potential of A, which is the potential on the shell minus the potential at point 0. And that would give you the potential inside the smallest shell. And so you do V A minus V to the 0 equals 0. And end up getting VA equals, well, it's, oh yeah, and V0 is 0. VA equals that. Because earlier, they told us to find the potential of the inner shell, and we did. And once you simplify this, it just turns out to be what is VA, and VA happens to be that. So VA happens to be that. And what do you know? It's the same. And that's how you do problem number 14.